Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 7, 2025, about 2 days ago. This paper unveils a unified, fully discrete diffusion large language model that delivers fast multimodal generation and understanding, including a reported 32 times text-to-image sampling speedup versus Lumina MGPT 2.0. The paper is titled Lumina-DiMOO, an Omni diffusion large language model for multimodal generation and understanding. And as we'll see later, the results are really impressive. Beyond speed, it supports text-to-image, image-to-image, and image understanding. And it tops open-source unified benchmarks with further gains from self-GRPO by 3%. Also, the authors shared a GitHub repo with full code and checkpoints. You'll find quick start install, inference scripts for text-to-image, image-to-image, and image understanding, plus in-painting and extrapolation. There is training code, a pre-tokenizer, configs, and multi-GPU sampling, a max logic cache, speed sampling, and examples help reproduce results. On Hugging Face, you'll find Lumina-DiMOO, weights around 8 billion parameters and safe tensors BF16, plus examples for text-to-image, image editing, in-painting, subject-driven generation, and image understanding. Alright, Figure 1 highlights what the model actually does and how well it stacks up. The collage shows working examples across text-to-image, image editing, multi-view, style transfer, and controllable generation, which signals broad task coverage. At the center, a radar chart compares unified models, and the larger shaded region indicates stronger scores across many benchmarks. On the right, an image understanding panel illustrates step-by-step reasoning for a simple cost problem. Well, Figure 2 compares 3 ways unified models handle text and images, and shows why the discrete diffusion route streamlines both speed and quality. The left panel depicts pure autoregressive decoding, which predicts the next token one by one, so generation is slow. The middle panel adds a diffusion head after autoregressive text, which can lift image quality, but complicates the pipeline. The right panel shows fully discrete diffusion with full attention, where masked tokens are predicted in parallel over refinement steps, enabling faster sampling and broader tasks. With that comparison in mind, Figure 3 shows how masked discrete diffusion unifies training and inference in one transformer, which predicts masked tokens in parallel, so generation is fast and consistent across text and images. The left panel presents training with masked text and image tokens, plus cross-entropy loss to recover originals. The right panel illustrates inference that starts fully masked, then refines tokens over several steps, producing either an image or a textual answer. Well, Figure 3 showed the parallel refinement process. Table 1 now spells out the special tokens that make that process multimodal and controllable. The table lists image and end image, plus task tags like canny, depth, open pose, and head, which mark control images. It also includes system, user, and answer to structure dialog. The end-of-line token preserves two-dimensional layout. The unconditioned token supports classifier-free guidance, which biases sampling toward the prompt without extra networks. So Table 3 reports text-to-image performance on the Gen-eval benchmark, comparing architectures and tasks under identical settings. The table shows the discrete diffusion model leading with an overall score of 88%, which tops both specialized generators and unified baselines. With self-GRPO, the overall rises to about 91%. The largest category gains appear in colors and attribute binding, which indicates better control over object properties, because the reward tuning strengthens semantic alignment. Alright, Figure 12 compares sampling time across generation and understanding, showing the discrete diffusion model is dramatically faster. The left panel reports text-to-image speed, where it matches Bagel, and, with max logic cache, runs about 2 times faster. Max logic cache means reusing confident intermediate results, so repeated refinement steps need less computation. The right panel shows smaller gains for image understanding, roughly 1.9 times, because decoding proceeds block by block, which adds overhead. Wrapping up, 2 takeaways stand out. A unified discrete diffusion large language model delivers fast, high-quality multimodal generation and understanding, with roughly 32 times text-to-image speedups and extra gains from the max logic cache, and reinforcement learning via self-GRPO tightens semantic alignment across tasks. The implications point to simpler, interactive, creative tools and scalable vision language systems. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.